recording is started.
That way neither one of us has to worry about it, since I half the time forget it.
Fair enough.
That end of it. So, yeah. Let's see here. I should be able to. Yep. Okay. Are you presenting any slides at all, or what?
No, I don't have slides. I've just got all of our parts sitting behind me.
Okay.
So I'll go through and talk through everything and go through
Okay.
and try to answer any questions you have.
All right. Do you by chance happen to have an open rocket or a Raz Aero?
I do have an open rocket, yes.
Simulation with the new motor?
The one that we tested?
Yes.
Yeah, I do.
Okay. And that will be the one that you will bring to the contest, correct?
So I mentioned this in the report, and I was going to double check with you today about it. So we would like to increase the length of our grains for a slightly more powerful motor. We wouldn't be able to static fire that before the competition. Would that be allowed or no?
No.
Okay, so we have to roll with the motor that we static fired.
Exactly.
Okay.
Yep. Now that doesn't say you can't static fire another one and send me the results.
Yeah.
If you can, then you'd have to build another contest motor based on that static fire.
Mm-hmm. Yeah. I'll
but
talk
I mean,
to.
Yeah, time's kind of running out.
Yeah, that's kind of where we're at right now. I'll see where we're at and see if we can squeeze out another one. If not, we'll go with the one that we tested.
Okay. Okay.
Do you want the open rocket file?
Yeah. Well, why don't we go through? Why don't you go through what you had planned for me first, then we'll come back and because I want to dig into the open rocket, and obviously things have changed.
Mm-hmm.
So thrust to weight ratios, all that kind of stuff have changed. I assume, given the other motor. So we need to. I don't have access to your technical report, so what she sent me was great as far as the static fire went.
Mm-hmm.
And our numbers matched up really well, which is good.
Yeah, it was really happy with that static fire. That went really well.
Yeah. So why don't you go ahead and get started, and if the other reviewers kick in, they kick in. If they don't, we just continue.
All right, sounds good to me. Just so you know, who's here right now, Peter Hall, the other one in the polo up there, he is our avionics lead, so he can answer any questions about electronics. Adam Butzine is my payload lead, so he can talk about anything to do with our payload. Ram over there is another member of our avionics team. Sawyer is our aerodynamics guy, and then we have our mentor, Todd Rocket Sensei Knight here as well, joining us. So that's everyone. So trying to get along with this. Sorry, I know this is probably really chaotic. All right, so here is our kind of motor setup and configuration. So we have a 64-inch motor case, as well as a boat tail and a nozzle carrier. There's our graphite nozzle there, and a forward closure. Both our nozzle carrier and kind of both ends are threaded closures, so everything just threads together. Because the grain stack that we're using is, I'm trying to watch the camera here. The grain stack that we're using is not as long as the actual case. We made this spacer here. So basically this just mimics a grain. Actually, no, sorry, I'm gonna try to do this another way because this is really more difficult than I was expecting it to be. So we've got this motor spacer here, and this just mimics a grain. So this will get put into our motor case on top of the entire propellant stack. And on top of the liner, it's got O-ring slots in it and a kind of lip there just to feed in. And it's all sealed off inside. There was a hole in there from when we did our static fire where we had our pressure transducer placed, but now that hole's all plugged up. And this is essentially just the size of a grain and the shape of a grain, obviously with no propellant in it. So it's just to take up space in the motor. With this, we can still screw on our forward closure like normal, and that is what screws into everything. So any questions on propulsion side of things?
No, I do the same thing.
All right, sounds good.
I've done I've done spacers, you know, the way you're talking about it, and there's a lot of ways to do spacers. So
Yeah,
just as long as the motor holds together, that's all we worry about.
yeah. I think we found a good solution. I think if we didn't have the spacer in there with the full propellant stack, we'd be going to about 55,000 feet, which, as cool as that would be.
Yeah, we would prefer you didn't do that. Can I just
Yeah,
can you just show me the aluminum tail cone that
yeah,
you
sure.
got? That is aluminum, right?
Yes, it is. Aluminum
Okay.
6061 with threads on the inside and a lip that just kind of holds our graphite nozzle.
Okay. Very good.
All right. As for our fin situation, we have a clamp-on fin can here. This is from Binder Design, Mike Snyder over there. This is made to fit our 4-inch case. We've test fitted it on and it fits on there pretty well. Kind of takes some time to make work, but this is our fin situation. We did fin flutter analysis a while ago, back when we were first ordering our fins, and we had pretty good numbers on that. I don't remember the exact numbers, but our fin flutter was not a concern with these fins. And I believe the manufacturer of those said he could get up to Mach 5 with those, which
Okay.
our numbers didn't necessarily align with, but our numbers were in a good place. I think we were going to about Mach 2, so we should be good on that end. So now getting into all of our systems and everything. So on top of our motor, and the way that our motor mounts in is this aluminum coupler here. So our entire design is transitioning from a 6-inch diameter to our 4-inch motor. And this is how that transition happens. This is essentially 2 aluminum pieces welded to this base plate here. When we originally made this, we had a mandrel down the middle, and then we turned the entire thing on a lathe just to make sure everything is perfectly concentric. So we're all kind of in the same axis. So this is really what does our transition. So our motor tube and our entire motor setup bolts up through that middle hole. And then obviously there's a hole on the forward closure, and a bolt just feeds through here and bolts everything on. That's a 3/8 diameter bolt, which is what we've always used in the past, and it's worked pretty well. So we're not too concerned about that breaking or anything like that.
Okay. How long is that shoulder where it bolt? How long are each of the? Yeah. How long is where that there?
This is a 6-inch section, and this is a 4-inch section. So
Okay.
they match the diameter of the body tubes,
Very
or
good.
I guess the tubes that go into them.
Okay.
Yeah, we ran a fair bit of FEA on this analysis just to kind of compare against everything with the entire thrust of the motor against a kind of static case here. So with the thrust of the motor pushing this way, we have a factor of safety of about 4 on this. So obviously, you know, that's not the real case, so we're not worried about this breaking at all, and we're pretty happy with how it turned out.
Okay.
So moving on from there, and I'm kind of going in the order that we're going to be integrating everything.
That's fine.
So we have our integrated systems bay here. This is the bay that holds our avionics bay and our payload bay. And we have our recovery bulkhead on top, but I'll get to that in a second here. So this just basically slides right down into our coupler, and then it's going to get nuts on the bottom to hold it secure. You kind of a better look at that. It's really just 4 carbon fiber rails with carbon fiber bulkheads on either end. And there are these blocks in here. Should have got one out. You can kind of see them there. Those have springs on them, so it's going to kind of keep both of our avionics and payload bays compressed really well. Those are really stiff springs. So once our bays are loaded in, they're not going to move, and they'll be completely accessible from where we need them.
Okay.
I'll grab the bays right now. So both of our payload and avionics bays are CubeSat form factors. Obviously, our payload bay for the the CubeSat form factor bonus, and then our avionics bay is also a CubeSat, just basically to fit in this system setup. So we'll start with avionics. Peter, you want to talk through this?
Yeah, so this is a 1.5 CubeSat, like Zach said. It's designed to be pretty modular, so we can swap things in and out. To go over like the critical things first, for our recovery electronics, we have 2 commercial flight computers, a telemetrum, and a stratologger. They're not mounted in here right now. We had to redesign some of the mounting hardware after some difficulties came up, but they'll just be mounted in those 2 slots on the left and right, bolted in there and secured properly. The connections leading off from those feed into those bulkhead connectors in the middle there. Zach, can you rotate that 90 degrees?
Yep.
So there is a locking connector there that's fixed into the aluminum bulkhead. So the flight computers plug into those. And then from there, we have our recovery harness going up to our recovery bulkhead. The reason for that is just to make sure that any load or stress that may be on that harness, either during flight or during recovery, is not distributed to the boards and is just distributed onto the much more secure aluminum frame.
Okay.
In terms of arming, so we're going to be arming with screw switches. So those are mounted actually on the integrated systems bay with wires leading down to there. So once you're on the pad, there's going to be holes drilled. There are holes drilled within the side of the rocket, so we can externally access these, reach in there, screw that, arm it, and then we'll listen for the arming signals, the beep codes from the flight computers to make sure everything is ready to go before we launch.
Okay. All right. Can you show me where the batteries are?
So the batteries for the flight computers again are those will be mounted. So those are not present in here at the moment. I can forward over drawings later if that'll be helpful, but essentially they are adhered. So we have two PCBs in the middle here. There will be two more on the outside, one for each flight computer. The batteries are going to be adhered to those with either command strips or epoxy, and then there's a 3D printed housing going over them as well. So we have both mechanical and adhesive methods of securing them.
Okay.
And those will
Okay.
fit into.
I'm having a hard time visualizing where the batteries are on that mounting on that cube.
Okay, so
where would they physically be mounted at? And how?
so yes, okay. So are you able to see the two printed circuit boards in the middle there?
Yep.
Zach, can you point those out?
Mm-hmm.
Yeah, one there and one
So-
there.
So each flight computer will have a dedicated board of those themselves. These they just haven't arrived yet, unfortunately. And on that board, so that basically stores the flight computer and the battery. The flight computer is screwed on there with short standoffs, and then the battery will be essentially glued onto there in some manner, either with epoxy or command strips, and then there'll be a 3D printed case that sits over top of the battery and then screws into that board as well,
Okay.
securing it on.
Okay, so in summary, the batteries and the two altimeters or flight computers, the battery is mounted on the same board that goes into one of those two slots and locked in place. And then the battery, there's a some sort of a 3D printed cover over the battery to secure it in place so it won't go anywhere.
Correct. Yes. So even if the adhesion failed, it would still be contained within there.
Okay, what's the delivery date for the, as you mentioned, the boards, you hadn't got them yet. What's the delivery date for them?
Sometime this coming week.
Okay, so in plenty of time for the contest.
Yeah, we will. Yeah, no, there should be no problem having those before the competition.
Okay, all right. Okay.
All right.
Would you like me to talk?
I like that design. I like the ability to pull cards out and replace cards. It reminds me of good old fashioned computers.
Yeah, that was sort of the inspiration, was to make it as adaptable as possible.
Okay.
All right. And now we'll move
Should we
on.
talk about?
Let me ask one question. You showed me
Yep.
only one. You showed me only one switch. I assume there's a switch per component, right?
Correct.
Should be
Yeah.
at
So
least-
every yes, the flight computers are entirely electrically isolated. So each one has its own battery, switch, and then dedicated
Got it.
the cable harness for recovery.
Okay, cool.
All right. And then we will, from there, we'll move to, or I guess we'll do a payload now because, like I said, the payload and avionics bays are going to be sitting in this same housing together. The avionics bay will be on the bottom and the payload bay will be on top. So, Adam, you want to talk through the payload real quick?
Sure. And I guess I'll start from bottom to top. So the idea of this payload is that there is a magnet. That red piece, it's inside that coiled wire is wrapped around that, and inside of that there is a magnet clamped between two concrete cylinders held together in tension on springs. So the idea is that during flight that will oscillate and generate some kind of voltage, and we're trying to read that voltage to see if it can see if the idea is to characterize what an axial electricity generator, how that would behave under flight conditions. And all the other stuff in there is just fixturing to hold it together and tensioning to hold the springs to the correct length. There's going to be a computer, Raspberry Pi in there to do our measurements and such. In that area, we haven't installed it yet. And also in that white box, we did an outreach event with a metro high school, and we told them we wanted them to design an experiment they wanted to conduct in the rocket, and they said they wanted to measure the state of matter of a non-Newtonian fluid under high acceleration. So if you were to open that box, you would see that they're hanging from the top. There is a force sensor, and then it'd be pretty difficult to take apart with your hands.
Yeah, don't take it apart. You don't have to.
All right.
Okay, I assume there's a switch for that to be turned on, or how is the electrical? How's the switches for the payload turned on, or where are they?
Did
our computer, so I'll have him answer that.
Yeah, so for this design, we specify the batteries. So the battery we chose to power the Raspberry Pi was sized appropriately to last for like 6 to 8 hours. So the plan was just to turn it on during integration and then leave it on until flight. Now, with the code written on the Raspberry Pi to record this data was written such that it's not going to start recording data, at least not at any high frequency. It will take very intermittent data readings, but it will not record a large amount of data until it measures an acceleration and starts the launch. So we won't have to sift through like 6 hours of data at the end. We'll be able to. It's similar to how the commercial flight computers record like a launch based on acceleration or change in altitude. We have a similar setup where we'll be able to just record most of our data during the critical period of the launch. But yes, the system itself is activated from integration until recovery.
Great. Okay.
All right. And then Adam, I believe, so this is your battery mounting system for that battery. You want to talk about that real quick?
It just kind of holds the battery in place like that. It's gonna sit on top of one of the metal plates and just be screwed in like that.
Yep. So.
Yeah, nothing too complicated to that one. And I believe the Raspberry Pi is going to mount the other.
I take it won't fall through under high G.
No, it's on pretty tight.
Okay.
All right. So that is there from the payload. So the way kind of our integration order is going to go is we'll load the payload and avionics bay into our integrated systems bay. We'll have the motor mounted to our aluminum coupler.
Mm-hmm.
And then we'll load the entire integrated systems bay with everything in it, all kind of screwed together down into the coupler. From there on out, so we don't have to, all of our kind of recovery stuff is accessible. So when we have to put in our ejection charges and all those things, all that is accessible kind of from outside the rocket. So we're not reaching our hands down to a body tube. That was kind of the motivation for this entire systems bay setup. So now then, I'll move to the recovery setup here.
Whoa. Okay. Yeah. No.
So we got a lot of stuff going on up here. So we've got our main U-bolt, which all of our recovery harness and all that stuff is connected to.
Okay.
Or I'm sorry, not the harness. The main, our main shock cord and all that stuff is connected to. And that's actually, I'll take this off. It'll be like 1 second here. All right, so we've got our main U-bolt here with a backing plate on it. two lock nuts to hold these on real well. So we're not at all worried about that becoming dislodged or anything. We've got our two ejection charge canisters. These are custom canisters, and as you can probably tell compared to a lot of them, these are really tall. The main reason for that was basically to push the blast of the ejection charges higher, or like kind of further away from the recovery bulkhead, because we are going to have some kind of electronics down here, which I'll talk about in a second.
Okay.
Then the other two things on here, I guess there's a few more things, but we have these two eye bolts, and these are going to go into the recovery system, which I'll talk about in a second here. And then just like we had on the avionics bay, we've got two more of these connectors, which are screwed into the recovery bulkhead, each with 4 wires coming out. So 2 of these wires will go to the ejection canister, and then 2 will go to the tender descenders, which will open up the main parachute. So we've got that double and completely isolated systems.
Okay. Okay, so that means you'll be having wires coming out from your electronics bay that will plug in, and so you can execute your matches and stuff, correct?
Yep. So we'll have here. I'll just use this one as an example. We'll have 2 wires going to an E-match in our ejection charge canister, and we'll have 2 wires going to E-matches in our tender descenders. Now, the tender descenders are what these 2 eye bolts here are for. And just to clarify, these all have washers and lock nuts on them, or they will have lock nuts on them. So we're not worried about these pulling out. So essentially the way that our main parachute releases is a piece of shot cord that wraps from one of these eye bolts up to the main parachute bag, essentially kind of wraps through it a little bit, and then comes back down to the other eye bolt. And on this other eye bolt, we'll have a system of 2 tender descenders with E-matches in them. So when one of those fires, that will release our main parachute out of the bag. So that'll release the shot cord, it'll kind of feed out, and then that releases the main parachute. And I can show you a little bit more about that. I've got kind of our recovery system down at the end of the table here, but I can show you all that in a minute as well.
Okay.
That's kind of the gist of it. All right. I'll show you this as well. So we have this piece here. This is a 3D printed bracket. So because we make the bulk of our structural components out of carbon fiber, we cannot have our avionics antennas in that carbon fiber section because we don't get any signals out of it. So our aerodynamic transition piece, which we use kind of to aerodynamically transition from our 6-inch to our 4-inch diameter, is made out of fiberglass so that we can feed all of our antennas down and we can get signals out.
Okay.
Now, last year we had all of our antennas and whatnot mounted directly to the transition. And I think we did end up having a problem with that in the safety review, and we didn't really like it just because, you know, things can get tugged on and all that stuff. So this year, we have this 3D printed mount here, which just mounts directly onto the coupler, and we'll have nuts on the back side of it as well. And it's being kind of sticky right now. Just kind of in an awkward position, but this would move all the way up. It would have nuts to hold it in, and then we have a bunch of holes throughout this to mount our antennas. We're going to have a camera mounted on here as well. Anything else on here, Peter?
Yes, the tele-GPS, one of our tracking methods, will be mounted on there as our primary tracking system.
Okay. That slips into the red tube that's over there. Is that what?
Yeah. So this just gets mounted on the threaded rods that hold the entire integrated systems bay together. It's being sticky right now because I think this is like a fresh new 3D print that we did for this. So we had good clean parts, but now it's coming back to bite me. Yeah, so basically that mounts onto the threaded rods, and there will be a nut holding it in place. And then the transition goes around it and also screws into our coupler piece.
Okay.
So kind of in our integration order again, once we have all the integrated systems bay connected, our harnesses going up to the recovery bulkhead connected. Then we'll move to kind of our structural setup. So we'll have to feed our entire recovery system through our body tube. And then once we do that, and we have our ejection charges in the canisters, we will mount on our transition and our body tube. So like I mentioned, the transition is fiberglass, 6 layers thick, and it just tapers down using an aerodynamic curve that our aerodynamics lead at the bottom there, Sawyer, that we kind of use CFD to get a nice curve out of that. And that gets mounted to the coupler, kind of the bottom half, and then the body tube gets mounted to the bottom half. We just have 3 screws that go through both pieces. They're ultra low profile screws, so we don't have to worry about them sticking out too far and messing with our flow. So those will just get mounted in there and everything will get screwed together. And another cool thing we have here, it's probably gonna be really hard to see, but you can see how there's kind of a shelf in there.
Mm-hmm.
So on that shelf, we'll have an O-ring that's flexible enough to kind of depress a little bit and compress. And we've actually measured it out perfectly so that if our recovery bulkhead is in the right place, which I believe is 2.225 inches above the top of the integrated systems bay bulkhead, then that shelf in there will seal our O-ring, and that will completely seal off our recovery, kind of our parachute region and the ejection charge region. So we're not going to have any escape of gases from that region down into the systems bay. We had a big problem with this last year, and we, after testing, we ended up getting a lot of our electronics dirty. This year we decided to do it this way, and during ejection tests and our test launch that we did, we had no problems with pressure in the top.
Okay.
So essentially it's just a shelf, it's like a L revolved, and that's just bonded actually to the body tube itself. So that kind of seals off the entire extra region, and then the kind of flat or bottom part of the L just presses down on an O-ring, and that seals off the bulkhead.
All right.
So that makes sure we don't lose any gases in our ejection. Moving on to the body tube, or the nose cone, sorry. So this just sits into the body tube as well. We have our 6-inch coupling region. These 2 silver bands here are shim tape because it was a little looser than we would have liked. So we added a little bit of shim tape, just kind of tighten it up a little bit and keep it real secure on there.
Are you going to shear pin that in place? Or
Yep, so it has 4 number 440 shear pins that will fit through the body tube and slide right into here.
okay, does the nose the nose cone does come off, right?
Yep, nose cone does come off.
Okay. All right.
And then it is attached to the recovery system. Should have a flashlight ready for this. 1 second. So essentially we have you can't see that at all. Essentially there's a bulkhead that's bonded about right here. It is about 3/4 of an inch thick, plywood with carbon fiber on it on either end. And it's kind of, the edges of them are curved off to match the curve of the nose cone. And that was put in place and then epoxied on with epoxy on the sides and a lip around the top. And on that bulkhead, we have a U-bolt that's mounted all the way through it. And that is how the recovery system connects to the nose cone.
Okay. All right. So, okay.
All right. And then the last thing I have here, I'm just going to move my computer over a little bit. Last thing I have here is our recovery setup. Fortunately, our recovery lead Trent can't be here today, but essentially this is what we've got. So this is our parachute bag that the main parachute is sitting inside of. This is our drogue parachute, which is just connected to the nose cone, and it kind of runs through the parachute bag. So once the main parachute releases, then the drogue parachute and the nose cone will fall away, and those will land separately. Our main parachute releases at about 1,500 feet. And that release method, like I said, is just the tender descenders. So you can kind of see these eyelets on here. We'll have shock cord running through these, and there's a few around this bag. The shock cord will feed through these in a certain pattern and come back down to the recovery bulkhead. And then once those tender descenders fire, won't be held on anymore, so it'll pull back through those eyelets and release the main parachute out of the bag. and release the drogue parachute along with the nose cone.
Okay. I'm looking at the open rockets that you sent
Mhm.
with your report too.
Mhm.
Okay, how am I going to do this? Okay, so the parachute that's closest to the nose, the tip of the nose is the main, or is that the drogue?
The one closest to the tip is the drogue. That's the small one, and then the bigger one is the main parachute with the bag in it.
And that one is housed inside the airframe?
The main parachute?
Yes.
Yeah. So it's going to be sitting like part way in the body tube and part way in the nose cone.
Okay.
And all this just sits above the recovery bulkhead. It might not be modeled super well in the open rocket. Really, a lot of our open rocket work has been, determining altitudes and
Yeah.
off-the-ground
No,
velocities.
I understand. Okay, so that means that the ejection charges gas has to go past the main and to blow the nose cone off, right?
Yep. So it's just one big region that the main parachute and the drogue parachute is sitting in. And when the ejection charges fire, it pulls the nose cone off, which pulls everything out.
Pulls
And we've
everything out being the drogue.
the entire thing. So we have, I guess the drogue and all the shot cord and the bag. And then at 1,500 feet, the bag releases the main.
Okay, how does the bag release the main? If I guess I'm trying to figure out. You mentioned that that you're using the tender descenders. I guess I'm.
Yeah, I got you. So on the main parachute bag here, there's these eyelets, or I'm sorry, grommets, and these are going to be folded in a specific pattern. I don't recall exactly how they're going to be folded, but essentially a piece of shot cord is going to run through each of these grommets, and that is going to hold the bag secure in tension. And then the tender descenders are going to be connected to that piece of shot cord on one end. So when the tender descenders fire, and we have two just for redundancy, so if one of them fires, it'll release it, or if both of them fire, it'll, same thing, it'll just release as expected. That shot cord will be released, and because it's all sitting in tension, it will pull back through these grommets. And once these grommets are kind of released, the bag opens up and the main parachute comes out.
Okay. So the tender descenders are actually inside the airframe.
Yeah, so the tender descenders will be. Bring it back over here. So the one end of that shot cord that runs through grommets will be mounted to this. It'll go feed back up through the grommets and then come back down to this other eye bolt. But it won't be directly connected to this eye bolt. The tender descenders will be connected to this eye bolt, and then the other piece of shot cord will be connected to the other end of the tender descenders.
Okay.
So the tender descenders are just basically acting like basically a removable chain link. So when the tender descenders fire, the shot cord will just slip off of the entire assembly.
Right. When the tender descenders fire, is there any chance that any of the pieces from the tender descender will wind up falling?
Yeah, so we're worried about that initially. We actually devised kind of a scheme where every piece of the tender descender has basically a piece of thread running around it. It's not just thread, it's I don't remember exactly what we're using for it. But basically everything is linked back into another piece of hardware on this recovery bulkhead.
Okay. All right.
So yeah, everything will be held secure.
Okay.
And then once those fire, the shot cord will feed all the way back out and release the main parachute.
Okay. All right. Okay, can you show me your shock cords
Sure.
and the lengths, how long they are?
I don't know the lengths off the top of my head. I
Does-
think it's give me 1 second here, sorry. I should be able to pull up a report here real quick.
You mentioned in the test flight that, while you're looking for this, you mentioned in the test flight that you had a recovery problem.
Yeah, we did. So essentially what happened was our shock cord was too long, and kind of in the descent, it got wrapped around the bag. And essentially that cinched the bag shut. So when the tender descenders fired, the shock cord released, but it couldn't pull all the way out because the kind of excess shock cord had wrapped around the bag.
Oh,
So to alleviate that, we shortened the relevant pieces of shock cord to prevent that from happening again. I think it was really just kind of an unlucky scenario with kind of how everything was situated in the air as it was falling, which obviously isn't great, but
hey, look at it this way. At least it happened there, not at spaceport.
oh, definitely, yeah, that's a lot better.
So the other thing is, maybe thinking of using some way of grouping your shock cords together with tape or rubber bands or something, so that they're not hanging loosely inside there. And
yeah, I think they may have actually changed some of that as well.
Okay.
Because this happened, well, our test launch was beginning of April. So we've had about a month to help alleviate any of those problems.
Yep. That's why we're doing this early.
Yeah.
Okay, shock cords. I
just pinged my recovery lead to hop on here. Or I'm sorry, no, yeah, my recovery lead.
I think you mentioned 30 and 40, if I remember right.
In the report?
Mm-hmm. At least in the initial one anyway, I think.
Yeah, 1 second here. Sorry about that. Yeah, so the cord keeping the deployment bag sealed, so the one that's connected to the tender descenders, that is 30 feet. So obviously then with that, it'll be sitting, I guess the main parachute bag will be sitting 15 feet above the nose cone.
Okay.
It looks like that might be the only thing listed in the report. I've got another
Yeah, that's
piece of.
that's okay. I'm sure.
Okay.
Sure. Again, your shock cords. Can you show me what you've got?
Yeah, sure.
And what I'm looking for is, has it been used before? Is there any sign of damage on it? Tears, fraying?
Yeah, I believe this is the same shock cord that we used for our test launch. And we kind of went through and inspected all of them, and they looked good. We did have a piece of, there's this as well. We do have this Kevlar sleeve that runs about 8 feet up the initial, like up from the recovery bulkhead, basically just to ensure that the body tube and kind of the sharp edge on the body tube can't cut the shock cord or damage the shock cord in any way.
Okay.
So through this, we have all the shock cord coming off, and also that just kind of groups everything together.
Right.
And this was something that got adjusted after the test flight. It just got kind of cleaned up a lot, and I think everything tightened up.
Okay.
So we have this. But yeah, it is. We are using shock cord, but we did inspect it carefully just to make sure there weren't any problems with it. And same deal goes with our bag. As you can see, it's a little dirty from our testing, but
That's
all
fine.
of our stitching still is good and all that's good. So
Okay. Now on your parachutes, any burn marks, any burn holes?
not that we found. We used a piece of Nomex, I believe, as a kind of a fire retardant from this, and the main parachute bag, kind of the way it fits in, acts as its own kind of flame retardant
Right.
to keep the parachute safe.
Okay. All right.
So-
The main reason I'm asking these kind of questions
Mhm.
that deal with the quality of the shock cords and the bagging and all that sort of stuff is you will be asked those same questions, and if the safety reviewers there think your shock cord may not hold up or whatever, they may ask you to replace it. So just as a heads up. Also,
All right.
I noticed you're using knots and all that kind of good stuff. Some of the guys will challenge you on knots and so forth. So just,
All right. Good to
be
know. Good to
aware.
know. Yep.
And also on your threaded rods, on your on your recovery
Yep.
recovery cords, or shock cords, be sure you know what the ratings on those are and the sizes. Like
Yep.
3/8 rod, good for whatever,
Yeah, I think we do have a lot of that information in tech report, and we definitely have it listed. I think we got them all from Chris Rocket Supplies, and we kind of based our sizing off of what our expected force and kind of the shock
Right,
from everything was.
I understand that, but you can't assume that a safety reviewer will have seen your documentation.
Okay.
Okay, so you need to be, just as a backup, just be able to discuss, the strength and the requirements and that sort of stuff. Okay, and
All right. Good to
and
know.
that will vary from reviewer to reviewer. Some reviewers do it, some don't. So, okay.
All righty.
All right. So I would like to now see your open rockets with
All right.
with the modified motor and look at thrust to weight, velocity off the rail.
All righty. 1 second here.
Sure.
Confirm that I have the correct Open Rocket file here. Alrighty. I will share my screen here. All right. Can you see our Open Rocket?
I can see. There we go.
Wonderful. All right. So this is our Open Rocket setup with the minor modifications to our motor and with the new motor that we're using. So
Okay.
this is simulated with the direct test data from our static fire, which is spinning an altitude of 33,000 feet.
Okay. Can you go to the simulation for me, the actual simulation tab?
Sure.
Velocity off the rail is 38 feet per second.
I think I may have a. 1 second here.
Do it edit on the sim.
Yeah. It's I've got it incorrect. That'll do it.
Yeah, change it
I've
to,
had this from
do me a favor and change it to 15 feet.
15 feet. Yeah.
Yep.
Aren't the Ezra rails 17 feet?
Well, but you don't have the full 17 feet.
Yeah, fair enough.
Okay. Okay, you're all right. Where are your rail buttons located?
We've got one rail button mounted on the. We don't have them modeled here. Can you see my cursor?
Yeah.
Okay. We've got one rail button mounted into the hardpoint coupler right here, and then we'll have another rail button that is essentially welded to our fin can.
Okay. Welded to your Oh, okay, right. All
Yeah,
right.
so we'll have a weld nut mounted on the fin can, and then we'll have a 3D printed aerodynamic shroud going over that, and then it'll just screw right in.
Okay, stability is about 2 3/4. That's okay. Go back to edit your flight sim again for me.
Yes.
All right, so, okay. I would suggest going ahead and, we're not gonna do it today, but you might want to tweak your your launch site for
Okay.
the actual spaceport.
Yeah, I
And
think it may have just gotten defaulted. We have ran them with the actual launch site coordinates and things like that, but yeah, we'll definitely be sure to run back through them again.
okay, what kind of average wind are you using?
I think I just used the default here. It was something similar to this,
Okay,
what you can see.
yeah, you may want to look at 15 miles an hour.
Okay.
And temperature is usually around 100 degrees, between 90 and 100 degrees. So you may want to adjust your standard atmosphere.
All right.
That's tweaking. That's absolutely tweaking. So
Yeah.
33,000, that's not bad. Your fins will definitely hold up to that sort of mock. Looks like your joint will. Thrust to weight. What is the thrust to weight? Must be.
I think it was about 7 from the report.
Okay.
Mass
All right.
motor is 93.2.
Okay. I think that does it for me. I think you guys are in good shape. You're going to have to do, you're definitely going to have to do some explaining on,
All right.
especially on the recovery side.
Okay.
I would expect lots of questions on that, just
Yep.
because it's a little, it's unique and it's relatively complex. So
Yeah, we're definitely used to that. Unfortunately, I didn't have my my recovery lead. I think is at work right now. So he could talk through it all a little better than me.
Okay.
So we'll be sure to get a better handle on that.
Yeah, that's fine. No, that's fine. For the initial flight review here, I think we're doing good.
All right.
I can't think of anything else other than just to remind you that based on that static test, that's the motor that you need to bring to the contest.
All right. We'll do.
So since you've been there before, you understand the environment and all that sort of stuff.
I think we're bringing about 20 people who went last year. So
yeah, okay. And you know the rules about going out to the pad. You have to be triply members and all that sort of stuff. Okay.
yep.
Let me, and obviously registration is bright and early, and that we're expecting somewhere around 130 teams with an average of about 10 members per team. So you can do the math, and everybody has to get registered. So
Yep. I think we may have one of the biggest teams this year. I know we were close last year. I think we're bringing 40 this year. So
yeah, yeah, exactly. So let me turn the tables. Anybody on the team? Do you have any questions for me? That pop up?
Peter, did you want to mention the telemetrum on the nose cone and all that stuff?
Yeah, so there's one thing we should maybe discuss quickly. I don't know if we mentioned this in the review so far, but the nose cone and the body tube land separately. And now this disconnection occurs at about 1,500 feet, so they should land pretty close together. And throughout the season, we are developing a custom radio GPS tracking system that unfortunately has not materialized yet. So our backup plan, and I believe I need to update this on the frequency allocation chart by the end of the month. But the plan we're working with is to keep the tele GPS on the rocket, and then have some sort of loud buzzer on the nose cone to help us identify it nearby. Would there be any issues with that sort of arrangement?
They actually want GPS on any falling part that's not tied. So one trick that I've seen guys do that when they blow their nose cone off is they will tether it back to the main part of the rocket, using some 1,000 feet of quarter, something like that. So I don't know if that's possible to do here or not, but that way they both come down within a reasonable. And I'm, by the way, 1,000 feet's not right, like 100 feet or something like that. Otherwise, you
Mhm.
may have to think about some sort of a GPS for the nose cone.
Okay, we'll make sure to be compliant with those rules.
Okay, all right.
All right, and I think the only thing I had was about propulsion, but I think that's sorted. So I cannot think of anything else. So I think we are all good on our end.
All right, you can stop the recording
All right.
and please copy